Hi everyone, I am Zhiwei, a fourth-year PhD student from UC San Diego. I will be the presenter for the first part of this tutorial, which will give you an overview of Embodied AI. In this part, we intend to give you an introduction to Embodied AI by answering the following questions. First of all, what is Embodied AI? And why should we study Embodied AI? Secondly, as many modern Embodied AI work involves the use of virtual environments, I'll briefly talk about why virtual environments. Next, I'll delve deep into the key factors of building such virtual environments. And finally, I'll give you a roadmap for the other 5 parts of this tutorial. To begin with, let's first talk about why embodiment is needed for AI. Take an example of learning to play soccer, for example, performing a penalty kick. It's pretty hard to learn it only by reading books or watching videos. You sort of have to try it out yourself, which involves using your own body to physically interact with the surrounding environment. And this is a typical example of embodiment. In fact, this embodiment can be very important in the process of developing human intelligence. As suggested by the well-known embodiment hypothesis in developmental psychology, the intelligence emerges in the intersection of an agent with an environment, and as a result of such sensory motor activities. More concretely, embodied AI is essentially the field that studies intelligent agents to solve tasks in the environment. Normally, the agents are able to see, usually in an egocentric view, talk either via text or audios, reason about their surroundings, plan and then carry out the necessary actions to perform certain tasks. While this field is highly interdisciplinary, it is largely driven by the computer vision community. For example, there are embodied AI workshops hosted at CVPR for the past 3 years. As embodied AI is the study of such agents to solve tasks, we will next talk about how to model these agents, the surrounding environments, and the tasks to be solved. Actually, there are several modeling approaches which will introduce in details in part 2 of this tutorial. But for now, let's just take a common approach, that is to model these entities by a Markov decision process, or MDP in short. In a Markov decision process, an agent receives observations from the environment, takes actions to interact with the environment, and obtains rewards that are reflective of the underlying tasks. For instance, in a navigation task, the rewards can be the minus distance between the robot and the target location. As you will see soon, many modern embodied AI work relies on the use of virtual environments. So let's ask a question. Why do we need virtual environments? Well, it turns out that learning in virtual environments has several major advantages over learning in real world. It is much safer to perform experiments in virtual environments. And it is much more affordable and therefore scalable to train agents in virtual environments. For instance, it is very risky to collect self-driving car data in real world. And it is not very affordable to have hundreds or thousands of physical robot arms, which is easily available in simulated environments. Okay, now that we've known why we should use virtual environments to study embodied AI, let us go through some of its key factors. We will first start with simulators. So what is a simulator? A simulator is essentially physics simulation plus sensory signal rendering. Physics simulation is a process that provides you with the mathematical model of how the underlying states change in the scene. For example, in the diagram shown below, how does these objects collide and move according to each other? On the other hand, rendering is a process that provides you with observation of the robot and its surrounding, given the simulated states from the physics simulation process. Well, there are so many existing simulators used for embodied AI research. To make your life easier, we would like to introduce several important things for you to consider when choosing a simulator to use. These factors include rendering, physics, speed of the simulators, their supported object types and properties, how do they model actions, and also what kind of human interfaces they can support. We'll go through these factors one by one. The first factor is rendering. In this section, we will introduce different types of sensory signals supported in the various simulators. Well, there are several common types of signals, including RGB, depth maps, surface normals, semantic or instance level segmentation masks, and optical flow. Here on the right-hand side of this slide, we show some examples from Maniscale, including semantic masks, surface normals, depth maps. There are also other uncommon sensory signals that are also important for you to consider. For example, the part level segmentation illustrated below on the left-hand side, which is an example from PointNet. In this example, each part of the desk and the chair is well labeled. This fine level, part level segmentation essentially can help agents to learn dynamics of articulate objects better. Another great example is acoustic signals, which are well supported in frameworks such as 3D World. So these acoustic signals can be helpful for advancing understanding, such as reasoning about the mass, textures, properties of objects. The second factor is physics. There's a spectrum of physical simulation, ranging from no physics at all, rigid body physics, articulated body physics, to soft body physics. In reality, different types of tasks require different granularity levels of physics. For example, visual navigation usually does not require full physical simulation because there is very few interaction involved between objects. But on the other hand, low-level object manipulation does require physics of a much finer level. And here we give two examples of low-level object manipulation, shown as first opening a cabinet door, which is manipulating an articulated object, and also pouring water, which is soft body manipulation. Another important factor is speed, which we refer to how fast the agent can interact with a simulated environment. This is quite important because it can affect what kind of training approaches are viable for the simulators. For example, you can do imitation learning with very slow simulators because it does not require a lot of interactions. While you can do model-based reinforcement learning with relatively fast simulators because the agent can use its internal world to reduce dependency on interactions. But for model-free reinforcement learning approaches, it usually requires you to have a very fast simulator since you're gonna need a lot of simulation, a lot of interactions. So you might be curious, So what are the factors that can have an impact on the speed of simulators? Well, the most obvious one is, of course, the speed of the underlying engines. But there are actually other factors that make optimizing or calculating, estimating the speed of a simulator quite tricky. For example, how complex the geometry is in your environment can have an influence on the simulator speed. Is the interaction of a coarse or fine level? For example, a high-level action is much faster to simulate than a low-level action. Or even, what is the resolution for the rendered images? Typically, a larger resolution can slow down the simulation by a lot. After considering rendering, physics, and the speed of the simulators, we would like to talk about what types of objects and what object properties a simulator can support. Let's begin with object types. So by the criteria of kinematic structure, we can classify objects into 3 categories: rigid body, articulated, and soft body ones. An example of articulated object is shown below on the left-hand side as a cabinet where the door can be opened. And on the right side is an example of pouring water, which entails soft body manipulation. As for the object properties, they're also pretty central to object interactions, especially for long horizon object manipulations. Here, when we say object properties, we refer to the actionable properties, such as the broken of a laptop from the AI tutor example. So in the left image, in the AI tutor example, when you hit the laptop screen, the screen will become cracked and the laptop will be labeled as broken. Another example is peeling or cutting properties of food or materials in general in VR kitchen. And you can see there is actually a fine level of state changes here. Finally, the example of temperature modeling is provided in the iGibson 2.0 environment. After introducing the actionable properties of objects, let's finally talk about the actions themselves. So the types of actions supported in a simulator sort of depend on 3 different things: the types of simulation, the types and properties of the objects, and also the types of the robots. So we've already covered the first 2 points in the previous slides. Now let's talk about the third one, the robots. Here we list several popular robots used both in the real world and in simulated environments. Namely, they're Fetch, Franca, Kuka, and UR. Besides them, there's actually a very large number of robots available in the real world. You can check this link below if you're interested. Well, a common concern for using robots in simulated environments is actually the trade-off between versatility and realisticity of a robot. A virtual robot can be very versatile and capable of doing a lot of high-level actions such as slicing, cleaning, which essentially eases the learning process for the agent, especially for long horizon tasks. But it comes at a cost of being not so realistic, because a virtual robot can have no physical counterpart in the real world. Next, let's talk about the action classification. So we can classify the actions into 3 categories: high level, low level, and somewhere in between. A low level action is illustrated on the right-hand side of the slide. And we take an example from Maniscale 2022, where the action is to pour water into another cup. And the actions are essentially motor controls that can be directly deployed into real-world scenarios. A high-level action, on the other hand, it is illustrated on the left-hand side from iThor. where the agent does not need to worry about motor controls or any low-level information processing. This type of action are usually good for learning to solve long horizon tasks. And an example API call here for the example shown in this slide is action put, object sprayer, and then object shelf. Also, there's a middle class, which is an example from Manipulator, which has a magnet-based grasping. The last important factor to consider for choosing a simulator is what types of human interfaces they can support. For example, Sapien, shown on the right side of this slide, has a nice human interface that people can do debugging or generate human demonstration by using mouse and keyboard. Another two great interfaces are virtual reality or VR, as in the example of VR Kitchen, and vision-based teleoperation, as shown in the paper called Single RGBD Camera Teleoperation for generic robotic manipulation. Now we're done with all important things to consider for simulators. Let's switch to the next key factor, assets. Assets are essentially data structure to be loaded into a simulated environment. It is pretty much an umbrella term, so here we will primarily introduce three types of assets, including object assets, scene assets, and demonstration of various formats. So the first example of object assets we would like to discuss is the grasping assets, including the popular YCB benchmarks and the recently proposed EGAD grasping dataset. These grasping assets are typically static objects used for training agents to perform grasping. While YCB has its advantage of being very realistic because it has the physical copy, EGAD, on the other hand, is of a much larger scale than YCB. The second example of object assets are those for general manipulation skills. Here we demonstrate four specific types, four specific assets, namely PointNet mobility, door jam, object assets from iThor, and object assets from Matterwork. So for PointNet mobility, it is a collection of diverse articulated objects. And door jam is a set of doors of different styles and textures to manipulate. Object assets from iThor, on the other hand, support several types of high-level actions such as slicing, cleaning, cooking, and so on. And finally, the object assets from Matterwork can support a lot of different general object manipulation skills. The last example is multisensory object assets, which is object assets that consider multisensory data. For instance, the object folder incorporates acoustic and tactile information for each object in this repository. And 3D World features realistic acoustic effects for object interactions such as collisions. And these sort of properties can help the agent to understand the scene better through advanced scene understanding. Apart from objects, we can also define scenes as object layouts. So in general, there are two types of scene assets, static scenes and interactable scenes. Here we have an static scenes example illustrated on the right side, taken from the Habitat Matterport 3D dataset. Static scenes are usually used for navigation-only tasks because all the objects in the scene are fixed. While on the other hand, interactable things, such as the one provided from iThor, can support a wide range of other tasks. So here, the example is that the objects from the same in iThor, where you can pour wine into different bottles. Another type of assets are demonstration, which come in several different formats. For instance, the state-based trajectory provided by Metascale, where the joint poses are recorded at each step for manipulation tasks. And also we have the video of human demos provided by the dataset called HOI4D. And example shown here is for a simple pick and place task. Also, we have other modality available, such as the dataset from Alfred, which provides step-by-step language description of the trajectory actions in the trajectories. And here, each high-level action is annotated with a corresponding language instruction. Well, with a simulator and necessary assets at hand, the ultimate goal in a lot of embodied AI work is to solve tasks. So now, next, we'll introduce several popular tasks in this field. We sort the example text into 4 categories, namely locomotion, visual navigation, object manipulation, and rearrangement. Notice that usually a category of task is not tied to a specific simulator or asset, but actually supported across different frameworks. The first example of locomotion is lagged robot control, where the agent needs to control a robot dog to perform a series of actions, such as spinning as shown in the diagram below. So this example here is taken from the paper called Learning Agile Robot Locomotion Skills by Imitating Animals. The second example is for visual navigation, which is one of the first tasks available in embodied AI research. So the example here is Object Go Navigation from the AI Habitat 1.0. The task essentially gives you a target object category and asks the agent to navigate in the scene, potentially memorizing the room structure to find the instance of such category. And the example goal shown here as to find the stool in the room is you can see that the agent observed egocentric RGBD observation from each of its frame, and actually also knows its relative position and orientation. Another example for visual navigation is actually visual navigation with language. So here we take the embodied question answering as an example. Embodied question answering is a task that, just like an extension of visual language, visual question answering, it asks the agent to answer a question about a given thing. But differently, this question usually requires the agent to navigate around the room or the scene to gather the necessary information to answer the question. For instance, here the question is, what is the car? What is the color of the car? And the agent needs to understand the question correctly and find the car first and then answer the question. Well, we give 2 examples of object manipulations, including Metascale 2021 and Subject. So Metascale 2021 contains tasks for manipulating articulated objects, such as opening the drawer or moving a chair to a specified position. On the other hand, Subject focuses on soft body manipulation, including folding a piece of cloth or pouring water. Notice that in Metascale 2022, we will actually add some of the soft body tasks. Another example of object manipulation is object manipulation with language. Here we take the Alfred challenge as an instance. And the agent is asked to interpret step-by-step human languages and to perform object manipulation and navigation accordingly. Typically, this kind of task features goals of long horizon, consists of a bunch of high-level actions. For example, here, the goal is to rinse off a mug and place it in the coffee maker. So the agent needs to first figure out where the mug is, perform certain actions with the mug, and then find the coffee maker, and so on. The final example is from rearrangement task. So here we take the AI tutorial rearrangement challenge as an instance, where the agent needs to navigate around a room to bring poses of multiple objects to their previous configurations. This task is usually quite challenging as it requires scene understanding, virtual reasoning, and object manipulations. For instance, the agent needs to first recognize the difference between two configurations, the old one and the new one, and then do planning to execute a sequence of actions to recover the specified configuration. Okay, let's take a summary of the part 1 in our tutorial. In this part, we've introduced the background of embodied AI as well as its several key factors, including simulators, assets, and tasks. Lastly, we would like to give you a roadmap for the remaining 5 parts of this tutorial. So in part 2, the basic structure, the basic frameworks and techniques for embodied AI, we would like to introduce the problem formulation, basics to RL planning, control / simulation, and introduce some environment construction examples. In part 3, design choices in modern embodied AI environments, we will introduce key design factors and present some case studies by popular embodied AI frameworks. In part 4, experiences and practices to debug simulator, we would like to talk about common issues in simulation debugging and also how to optimize your environment. In part 5, real robot and sim to real transfer, we would like to discuss causes of the domain gaps and also some techniques and tips to address such sim to real gap. And last but not least, in part 6, embodied AI tasks in Metascale and visual learning challenges, we will give you a summary of the Metascale 2021 challenge and give you a preview of the incoming Metascale 2022 challenge. And that's about the part 1. That's all about the part 1 of this tutorial. Thank you.
Hi everyone, I'm Fanbo Xiang, a PhD student from UC San Diego. Let me present the second part of this tutorial, the basic frameworks and techniques for embodied AI. Let's start from an overview. In this section, we're going to talk about how the embodied AI community models and solves problems, how simulators and environments are built, and how to build your own environment. This section is for all people who want to build or use embodied AI environments. We have 3 main topics: modeling and approaches for embodied AI, simulation technology for embodied AI, and building an environment from scratch. Let's start from the modeling and approaches. In this section, you will learn the basics of world model, learning-based methods to solve tasks, as well as classical robotics. Let's start from a very general question. How do we model the world? In the 17th century, Isaac Newton gives an answer with his laws of motion. Let's imagine the world has only a single object, a particle with mass. If we let x be its position, and we use the dot notation to represent the time derivative, so x dot is its velocity, and next double dot is the acceleration. Newton's second law states that force acted on the object equals its mass times acceleration. This is his model of how the world changes under external action. If we call the position and the velocity the state of the world, the force and action on the world, we can say that Newton's second law models the transition of state under action over time. Now let's consider a more complex world in an embodied AI task, pushing a block to a target location with a robot. In this case, we can define the state of the system as a configuration of the world. Here, the state includes joint angles θ1 to θ7, block position and orientation, as well as target position. The collection of all states is called the state space S. Similarly, we define the robot command as an action. For example, here, the action can be the motor torque, which is used to control the robot. We call the collection of all actions the action space A. Next, we can also use a transition function T to describe how state changes over time according to an action. Formally, T describes the rate of change of the state, given the current state and action. In our robot example here, T is governed by classical mechanics. The two examples have shown us that we can model the world with the three tuple S, A, and T. We call this the forward model. S is the state space, which includes all possible world states. A is the action space, which includes all possible control signals. T is the transition function, which describes the environment dynamics. For what we have seen so far, the states are changing continuously, but on a computer, things are discrete. Here, we can discretize the transition function over time. Now, we can write st plus 1 is equal to a discrete time transition that takes st and at. And in general, the transition can be stochastic. That is, the transition function gives the distribution of the next state instead of a deterministic one. Now we've seen the forward model of the world. The next question is, how do we define the success of a task? How do we know if a task is complete? A straightforward idea is to define success on states. In the robot example, we can say that it succeeds if the box XYZ is close to target XYZ. We may also require that the box velocity is close to 0 and the robot velocity is also close to 0. More generally, we can introduce a reward function R to measure how successful the current state or action is. For example, we can make the environment to give a reward of 1 when the block is close to the target and 0 otherwise. The four tuple here, S, A, T, and R, is formally known as the Markov decision process, or MDP for short. So on top of the forward model, MDP adds the reward function to describe how successful the state or action is. Now, we have the world model and the success condition. How do we solve tasks? To solve an embodied AI task, the agent needs to know what action to take given the current state. And this is called a policy. A policy pi takes a state and outputs an action, and it can be stochastic. A good policy should eventually complete the task, that is, reaching a successful state or accumulating a great amount of reward. There are roughly 3 main branches of ideas to find a good policy. First, we can imitate from an expert. This is called imitation learning. Here, the transition and reward are not required to be modeled for this method. Second, we can learn to accumulate reward in MDP. One example is reinforcement learning. It is called model-free RL when the transition is not modeled, and model-based when the transition is learned in the process. Finally, we can use our knowledge of mechanics to design rules. This is a popular method in classical robotics. Here, the transition is typically modeled in advance. Some methods would use learning to get a model and then apply classical robotics to solve the problem. Next, let's talk about learning-based methods, specifically imitation learning and reinforcement learning. Learning-based methods aim to find the optimal policy to the MDP, which is defined as follows. For a given policy, pi, we run the policy on the environment for h steps and collect rewards. An optimal policy is the one that maximizes the expected cumulative reward. That is, the summation of reward over h time steps. We know in practice that a discount factor is often used to handle the case where h could be infinity. It is not discussed here for simplicity. Let's see an optimal policy for the previous problem. The environment gives a reward of 1 when the block is close to the target and 0 otherwise. Let's also assume that the system is terminated when the reward is 1 or the task is complete. An optimal policy for this example is one that eventually moves the block to the target position. Another important notion in practice is the partially observable MDP, or POMDP. In practice, the state is not always known. Instead, we get some observation. For example, the state may be the position of the cube, but we only get an image of the cube. That is the observation. And common types of observations would include RGBD images, the position and velocity of objects and robots, task information, such as the goal position, and other sensory readings. To simulate an MDP on a computer, people in the community often use OpenAI James interface. In this interface, we will call reset to initialize the environment and get the first observation. Next, we run the policy to get an action. And then we call step with the action. The step function is a combination of transition and reward of the simulated MDP. Here, environment builders would implement the m.reset and m.step functions. And task solvers would use this MDP to develop policies. So as a task solver, how do we find a good policy? The first idea is to assume that an expert, such as human, has already solved the task and mimics this behavior. This is imitation learning. The second idea is to interact with the environment and try to improve the policy with the experience. And this is reinforcement learning. For imitation learning, the input is a set of state action pairs that is generated by experts. Imitation learning tries to predict the action based on the state. So we can use supervised learning here. On the other hand, what if we do not have expert data? In this case, we can learn by collecting interaction experience. First, the agent interacts with the environment to collect experience, including states, actions, and rewards. Next, the agent uses collected experience to improve the current policy. By repeating this process, the agent gets a better and better policy. And this procedure is known as reinforcement learning, or RL for short. Reinforcement learning is a large family of methods. Here is a taxonomy for it. You may refer to this intro to RL made by OpenAI for details. We may also combine reinforcement learning with expert demonstrations. Thus, give rise to the learning from demonstrations methods, including offline RL, which trains RL with given experience without further interactions. Augmenting online RL training with demonstrations, dynamic movement primitives, and learning transition model from demonstrations. Now, let's move on to classic robotics. A popular pipeline in classic robotics is planning and control. For example, if you want to move a block from the left to the right, we will first use motion planning to generate a trajectory. That is, a position, velocity, and acceleration sequence of the robot. We will then use control to execute this trajectory. Let's first talk about motion planning. Motion planning tries to solve the task of moving robots from one pose to another. In motion planning, we assume that we know the start and the goal of this robot. We also assume that we can verify if a random pose is valid. That usually means collision-free. We also need to be able to verify whether a pose is reachable from another pose using some simple control strategy. Common algorithms of motion planning include the Rapid Exploring Random Tree Algorithm, or RRT, and the Probabilistic Roadmap Method, or PRM. Next, I'll take PRM as an example. This is a two-phase algorithm. In the first phase, it is map construction. We will first randomly sample collision-free configurations, then connect every sample state to its neighbors, and also connect the start and goal state to the graph. The second phase is the query phase. Here, we can just find a valid path using some simple search algorithm like Dijkstra. However, for some tasks like grasping, we need to move the robot gripper to a position. But motion planning often takes a robot joint pose as its goal. So how do we find the robot pose of a given gripper pose? It turns out this is a well-studied problem called inverse kinematics, or IK. For example, in our simulation platform Sapien, it takes 2 lines of code to compute the IK for a given robot. After finding a path with PRM or RRT, let's say it is a path of joint positions QD. A time parameterization algorithm would convert this path to a trajectory, which also contains velocity and acceleration to prepare for the control step. With the trajectory generated, we are now ready for control. Robotic control takes a given trajectory and tries to follow it by controlling joint torques tau. Similar to F equals ma, the dynamics of a robot is known. The process of inferring joint acceleration from joint torque is known as forward dynamics. And the process of finding the proper torque from desired joint acceleration is called inverse dynamics. We can see inverse dynamics consists of 3 terms. The first term is similar to F equals ma, but here M is replaced with the inertia matrix. The second term only has effect when the robot has non-zero velocity. The effect is modeled by the Coriolis matrix. The third term summarizes effects of external forces, such as gravity. Now we know the desired acceleration from the trajectory, and we have the formula for inverse dynamics. Ideally, by computing tau from the desired acceleration, we should get a perfect trajectory. However, the real world is not perfect. So what if there's some error on the joint position? To mitigate this error, we can use another control method called PD control. In PD control, the applied torque is proportional to the velocity arrow E dot and positional arrow E. Intuitively, when the position lags behind, we just increase torque to catch up with the position. And similarly, if the velocity is too slow, we also increase the torque to catch up with the velocity. We can see that here, inverse dynamics is not used at all. So is there any problems? Well, it turns out that the PD control does not guarantee the convergence of E. And even when the error converges, it is often non-zero. The way to fix it is by combining both inverse dynamics and PD to form the augmented PD control, where PD is only used to mitigate the residual error from the inverse dynamics controller. The augmented PD control will converge to zero error if the robot is modeled correctly. Another way to correct any steady-state error is by adding an integral term to the PD. This is called the PID control. And there is also the augmented PID controller, which is more tolerable to inaccurate modeling of the inverse dynamics. Now let's see an application of PD controller in embodied AI environments. You may hear people say that their environment uses a PD velocity controller. What does that mean? It really means that we are trying to use a PD or augmented PD controller to follow a constant velocity trajectory. Here, since the velocity is constant, the acceleration is 0. And we do not care about position error. So the augmented PD control becomes the inverse dynamics of 0 minus the velocity error term. This can be easily implemented in Sapien as shown in the code below. Control can also be used in MDP modeling. You may see the RL paper claim we use velocity control or position control as an action. What does that mean? Here, they're really saying the action in the MDP is target joint velocity or target joint position for a controller. A controller such as PD is used to convert this velocity or position signal to joint torques, which are then used to drive the robot. They make this design choice because velocity or position may be a better choice for MDP action due to learnability and sim-to-real transferability. To conclude the control part, I'd like to mention that control is a huge topic. Most control methods focus on the stability and robustness. There are many branches, such as optimal control, feed-forward feedback control, robust control, self-organizing control, and stochastic control. Optimal control also has a strong connection with reinforcement learning. Okay, let me summarize embodied AI approaches here. First, there are learning-based methods, including imitation learning, which uses expert demonstrations, and reinforcement learning, which improves policy with interaction experiences. Next, in classical robotics, we have introduced motion planning, which moves the robot between configurations, and control, including PD controllers and its variants. A good resource for learning more on these topics is the course Machine Learning for Robotics by Professor Hao Su at UCSD. And here's a link. Now, how do we study embodied AI algorithms and design new approaches? First, we need an environment to do so. As discussed in the intro, we may use real or simulated environments. Real robot may have high costs and safety concerns, while for simulations, we need to understand the techniques and limitations of them, such as physical simulation, camera simulation, asset loading, and problems in sim-to-real. So for the next topic, we are going to take a look at the simulation technologies for embodied AI. This topic includes an overview of simulators and environments, and the important techniques. Okay, from simulator to environment. Here, we define a simulator as a library, often a simple SDK, that simulates one or more physical processes, such as a rigid body, particle system, or light transport. Examples of simulators include the engine of Mujoko, the solver of Flex, and the bullet physics SDK. Next, we call a software that bundles together simulators to help developers as an engine. For example, the game engine Unity, Sapien, and PyBullet. Many people do not make the distinction and would call all these engines a simulator. Next, when we say environments, what we really mean is bundles of engine or simulator assets and tasks for studying specific embodied AI problems, such as AI to store, many-skill, or AI habitat. Do note that many people will still call environments as simulators. So the real content of a simulator really depends on the context. Here, I give a summary of our classification of different simulation software and assets. On the low level, there are basic graphics and physics SDK, such as OpenGL and PhysX. On the mid level, there are engines such as Unity, Sapien, and Mujoko. On the high level, environments bundle together assets into engines and define embodied AI tasks. Our group has made many contributions to the embodied AI community by building the Sapien engine, the PointNet mobility dataset, and many-skill environment. If you're wondering what software you should choose, here is a guideline. You can use graphics and physics SDK directly if you are creating or modifying an engine. You can choose an engine if you want to create a new environment. And you should pick an environment if you want to solve a predefined embodied AI problem. The next topic is rigid body simulation. You probably have heard of these simulators, like Mujoko, Bullet, or PhysX, and you may be wondering what they are doing under the hood. Well, these simulators are able to simulate the motion of objects. They handle collisions between objects. And they handle connected bodies with customized constraints. In fact, most rigid body simulators repeat the following steps: integration, collision detection, and constraint solving. These steps happen within the step functions of simulators, such as PyBullet step simulation function and Sapien Syn step function. Let's take a look at them in detail. First, integration refers to advancing the simulation time and updating simulation states. A very common choice is the semi-implicit Euler integrator. That is, update the velocity with acceleration and update the position with the new velocity. Collision detection refers to the process of finding contacts between bodies. The collision detection algorithm finds the contact positions, normals, and penetration distances, then adds them into the list of constraints for the solver later. The collision module is often completely separated from the constraint solver module. The constraint solving makes sure no physical restrictions are violated. For example, bodies connected with joints should move correctly, and bodies in contact should not penetrate each other. The constraint solver solves a system of equations or an optimization problem to figure out a proper force or impulse to add for each constraint. A key parameter is the solver iterations, which indicates how long the solver is allowed to run, and can greatly affect the stability of simulation. Next, let's talk about camera simulation. Camera simulation is achieved by rendering, which tries to model light transport. Important components in camera simulation are cameras, lights, geometries, materials, and textures. In camera simulation, the camera imaging process is typically much simpler than the real one. The real cameras will use lenses, which can cause deep focus blur, but simulations typically use a simplified pinhole camera model. Another important feature in simulation is the camera frustum. Many simulated cameras have a range limit defined by a near clipping plane and a far clipping plane. Objects in front of or behind the frustum will be completely invisible. For example, the cube in front of the near clipping plane will be completely invisible instead of blocking the camera. The next component in camera simulation is the lights. Common types of lighting include directional light, like the sun, point light, like a lamp, spotlight, like a flashlight, ambient light, modeled by environment maps. The effect of these lights are shown in the pictures rendered by Sapien on the right. There are other types of lights, such as area light emitted by a wide white screen, or indirect light from interreflections. These lights are harder to simulate and often require complex techniques such as costly ray tracers to render. After cameras and lights, how do we represent objects? Here, we need geometry, material, and texture. Geometry, such as mesh, curve, and volume, represents the shape of objects. Material describes the reflection and refraction properties of objects. There are physically based rendering material models, such as microfacet models, and heuristic models, such as the foam model. Textures are used to describe the spatially varying material parameters over the geometry. Concretely, in the shading pipeline in the Unreal Engine, the quad is the input geometry. The computation pipeline in the middle is describing the material. And some material properties are specified by textures. Let's move on to talk about assets. Here, I will focus on the technical aspects, including file formats, representations, and usage. Assets, such as objects and things, are crucial components for embodied AI environments. For static things and objects, people use 3D model formats to store them. Here is a list of the formats supported by most software, so they are called exchange formats. And in general, I recommend using the GLTF format to store your models when possible. The OBJ format has a bad compatibility because it's stored in plain text. And STL format is excellent for shapes without material, such as collision shapes. The 3D model formats are not designed for robotics. To represent robots, the most popular choice is URDF, or Unified Robot Description Format. It includes kinematics and dynamics properties, in addition to the meshes and the materials. URDF uses the XML format. In it, a link tag represents a rigid part, which can have properties such as inertial, collision, and visual geometries. A join tag represents a connector for two links. There are many types of joints, including revolute, continuous, prismatic, fixed, floating, and planar joints. Except for floating, each joint type would restrict some degrees of freedom of the connected bodies. Assets are not useful until they are imported into simulation environments. If we are using a low-level physics or random SDK, async is probably the best library. If you're working with engines, different engines have different choices. For example, Sapien and PyBullet can load assets dynamically. Mujoko loads URDF or their own MJCF format all at once. Game engines such as Unity have excellent editor with GUI for importing assets, but loading assets programmatically may be a lot harder. If we're trying to customize existing environments with new assets, you should check whether the environment is designed to support such operations. And environments will typically inherit the asset loading procedure from their engines. To summarize, in this section, we have learned different types of simulation software. Basics to rigid body simulation, camera simulation, and how to use 3D assets. To put the knowledge above into practice, let's build an environment together from scratch. Let's build an open cabinet environment. First, we need to decide the task. Here, our task is to open the door of a cabinet with a robot arm. Next, we need to define the assets. We can use this cabinet and robot shown here. They are both in the URDF format. Next is to decide the controller. The options include torque control, PD velocity control, a combination of controllers, or non-physical processes such as teleporting the arm. Here, we will show PD velocity control. Next, we decide the type of object interactions. How will the robot open the door? We can use physical processes such as force and friction. Or we can use a simplified model. Glue the robot to the door when it is closed. Or we can make the door opening even simpler. It opens automatically when the gripper is closed. The choice really depends on the scope and definition of tasks. And all the choices above can be useful in certain situations. Here, we will show the physical process. Next is to decide the observation space. Should we use some simulation state? Should we use an RGBD camera? Or maybe both? Here, we will use the RGBD camera plus the robot state. The next step is to choose a suitable framework. Here, we use Sapien. First, because we made it, and it has a very good debug viewer. It also has a clean API, type hint, and code completion. So it is very suitable for education. Now it is time to start coding the MDP. We follow the gem interface to write reset and step. The render function is mostly for visualization. Next, we initialize Sapien with some standard boilerplate code. The most important thing in building an environment is visualization. So we implement the render and write a main loop for running the viewer. Now, we're ready to load the assets into the simulator. We first add lights so we can see the objects. Then we load the ground, robot, and cabinet into the scene. And we add physical steps into the main loop. Now, we can immediately see from the visualization that the position and the scale of the cabinet are not reasonable. So we can move on to debug these assets. While it is possible to compute the bounding box in Sapien and rescale the asset, here I just use the pre-computed numbers to make the cabinet more reasonable. Next, we implement the reset function. Here, we initialize the states of the robot and reset the controller. Next, we implement the step function, which combines the transition and reward function in an MDP. Here, we need to decide how many simulation steps to take in env.step after each action. For example, if we run the physical simulation at 500 Hz and we want a 20 Hz action, the step function should step the simulation 25 times. In step, we implement the augmented PD velocity controller as introduced earlier. Now, it is time to implement the observation. Here, we want to capture RGBD images from the scene, so we add a camera. It is important to verify the added camera is working as intended, so we visualize the captured images. Sapien also draws the illustration of the added camera in the viewer for easier debugging. Here, the camera are represented by the lines in this viewer image. We finish the observation implementation by adding the robot states. Now, we need to decide what reward to use. For example, we can use sparse reward. That is, we give 1 when the environment is successful and 0 otherwise. Or we may implement dense reward. For example, make the reward proportional to the cabinet door angle, or even give some reward based on the distance of the gripper to the door handle. Here, we have the sparse reward implemented. To test the reward implementation, we can again use Sapien's viewer. Here, we can manually drag the joint angle to open the door and inspect the reward by printing it. Next, the GIM interface requires a step function to return done and info. We can set done to true when the task is completed. It is also okay to never set done to true. Finally, for many algorithms, it is important to normalize the action. Therefore, the environment should specify the range of actions. Here, we use -0.2 to 0.2 for all robot joints. Now the environment is complete. We can test it by executing random actions and observe the results. The full code will be released after this tutorial. So are we done? Well, no. Here comes the most important part, iterate. Developing environments is an iterative process. We will first develop the environment following this tutorial, and later, when we are solving the environment, we're going to find the issues. Then we need to analyze the issue and see if it's caused by the environment, and we may need to modify the environment if needed. For example, the environment we built above probably will not work because I use the default friction, which is too small for the gripper to hold the door firmly. We will introduce common issues in the later section, experiences and practices, to debug simulators. To summarize this section, here is a flow chart for the steps. To build an environment, we need to decide the task, decide the assets, decide the controllers, decide the object interactions, decide the observation space. Then we pick a framework, implement the MDP, and finally test, debug, and iterate. Okay, thank you for listening to this section, and here is my contact information. And you can send me an email if you have any questions on this part.
Hi everyone, my name is Jiayuan Gu, a PhD student at UCSD. This section is the part 3 of building and working environments for embodied AI. In this section, we are talking about how to design embodiment, how to define a task, what kind of assets are needed. We will show several case studies of existing embodied AI environments. This section is intended for who want to find a suitable environment to start their projects, have a deeper look at environments they are using, customize or create a new environment. All design choices are discussed in the simulation context. Here, we list some common design choices. The most common design choices in building an embodied AI environment are embodiment, task, and assets. According to the theory of embodied cognition, many features of cognition are shaped by aspects of an organism's entire body. Sensory and motor systems are seen as fundamentally integrated with cognitive processing. For an intelligent agent, there exists a path from sensoring to interacting with the world. Sensors perceive the physical world and send signals like images to the agent. The agent acts upon sensory information and outputs a command to actuators. The actuators equipped with the robot translate the command into what the robot can understand. For example, active joint talks. The robot is the physical body with various sensory motor capacities. It restricts what kind of sensors and actuators can be used, and therefore shapes the cognition and action. Here we list 4 common types of robots: legged robot, manipulator, wheeled robot, and a mobile manipulator. Take the mobile manipulator Fetch, for example. It consists of a mobile platform, a head to mount cameras, a torso that can lift, an arm with 7 degrees of freedom, and a 2-finger parallel gripper. Next, we will discuss sensors. There are several common types of sensors. For example, a robot can use mounted cameras to perceive visual information. it can make use of its motor drives to perceive the movement of its arm, which is a kind of proprioception. And it can also leverage GPS and compass to perceive its ego motion. If the robot hand is equipped with force sensors, it is able to perceive tactile information as well. Visual perception includes RGB and depth images, semantic and instance masks. There are also other types, for example, normal and optical flow. Apart from types of signals, placement is also an important factor. Commonly, cameras are mounted on the head and arm of the robot, or at a fixed position relative to the robot base. Different camera placements can affect cognition. For example, the arm camera can provide a closer look at the target to manipulate, with less occlusion. Proprioception refers to perception or awareness of the position and movement of the body. It usually includes the joint states and end-effector pose. To manipulate objects, it's helpful to know the contact between the gripper and the object. We can check whether the gripper is grasping something by measuring the contact force in the simulation. There also exist force-torque sensors, which can measure external force and torque applied to a joint. GPS and compass are widely used in navigation tasks to provide ego motion information. They enable the agent to localize itself relative to its initial pose. We summarize design choices for sensors here. We have briefly discussed the types and placement. In addition, specification is taken into consideration sometimes as well. An example is the camera resolution. Next, we are talking about actuators. An actuator is a component of a machine that is responsible for moving and controlling a mechanism or system. An actuator takes an input command from the agent and outputs commands to the simulator to control the robot. For instance, the input command is move forward, and the output command can be to set the base position 0.1 meter forward along the x-axis. Besides, the output command can be low-level physical signals. For example, 10 Nm of torque applied to the wheel joint. Here, we show an example of actuators implemented in Manipulasaur. The base actuator takes a discrete action as input, say, move forward, and sets the robot pose to a pre-computed navigable grid position on the floor. This process is non-physical. Similarly, the arm actuator receives a discrete action, say, move wrist along the positive x-axis. It then computes the target joint positions by inverse kinematics and controlled joint motors to reach those positions. The gripper actuator is implemented as a magnet, and the object can be snapped to the gripper if they are close enough. This process is non-physical as well. Next, we are talking about task specification. It includes goal specification and how to define success metric. The task is considered completed if the goal is achieved. In general, the goal should be provided in or perceived from sensory information. We list several common types of goal specification, including geometric position, object category, semantic or instance masks, language instruction, Go image, successful demonstration. For example, a goal specified by a language instruction can be a sentence, say, find white mark. The agent needs to pass the goal, navigate through the room, and recognize the white mark. We also need to design a success metric to measure whether the goal is achieved. For example, a navigation task is completed when the agent stops close enough to the goal, and a manipulation task is accomplished when the pose of the target object is close enough to its goal. Sometimes, additional requirements need to be satisfied, especially for manipulation. For instance, the robot should be static or successfully reset its arm. Different tasks need different types of assets. There exists many large-scale, non-interactive scene datasets, like Replica, Gibson, Matterport 3D, and etc. They are suitable for navigation. For manipulation, rigid objects and articulated objects are needed to support interaction between the robot and the environment. We have briefly described the common design choices to build an embodied AI environment. Let's have a quick recap. Embodiment lays the physical foundation by specifying the robot hardware, sensors, and actuators. Task specification describes the objective and how we measure to what extent the objective is achieved. Assets build up the environment with which the robot interacts. Before case studies, we would like to discuss physical versus non-physical simulation. Certain design choices do not need physical simulation. For example, a high-level command, pick an apple, is usually implemented by setting the position of the apple at the gripper without physical simulation. Non-physical simulation usually makes the implementation easier and faster, but at the cost of fidelity. In the following sections, we present case studies about 3 environments: AI habitat, AI to SOAR, and many-skill. Note that the cases studied here are not exhaustive. There are also other embodied AI environments, like behavior, MetaWorld, RoboSuite, RO Bench, 3D World, and etc. Let's have a look at AI Habitat. AI Habitat is proposed by Meta AI. Habitat 1 is intended for navigation. Point goal and object goal navigation are 2 widely studied tasks. It also supports instruction following and embodied question answering. Habitat 2 features mobile manipulation and introduces the Home Assistant benchmark. The Home Assistant benchmark includes 3 challenging long horizon tasks. The video shows an example of the task set table in the benchmark. In this talk, we focus on Habitat 1. The robot is abstracted as a cylindrical primitive shape with a diameter of 0.2 meter and a height of 1.5 meter. It is equipped with a RGBD camera at a height of 1.5 meter and oriented to face forward. It assumes perfect GPS and compass sensors, which can be used to compute the goal position relative to the agent. Here is an example of visual perception, including RGBD images and semantic masks. The agent can take one of 4 discrete actions, namely move forward, turn left, turn right, and stop. The movement is implemented by setting the pose of the virtual robot without physical simulation. Navigation constraints and collision response are based on navmesh. A navigation mesh is a collection of 2-dimensional convex polygons that define which areas of an environment are traversable by an agent with a particular embodiment. A navigation mesh is usually generated for each static scene offline, which can be used to compute navigable positions at a given height efficiently. Next, we will describe 2 navigation tasks supported by Habitat, namely point goal navigation and object goal navigation. For point goal navigation, the goal is a 2D position relative to the agent start location. An episode is successful if on calling the stop action, the agent is within 0.36 meter of the goal position. For object goal navigation, the goal is specified as an object category. For example, finding any stone. An episode is successful if on calling the stop action, the agent is within 1 meter from any instance of the target object category, and the object can be viewed from an oracle. Beyond the success rate, SPL, short for success weighted by path length, is also widely used to measure the efficiency to reach the goal. Habitat 1 supports many non-interactive scene datasets, like Gibson and MetaPost 3D. Next, we are talking about AI2SOAR. It includes iSOAR, which can support navigation and high-level object interactions, instruction following, as well as embodied question answering. It also includes ManipulaSOAR, which focuses on mobile manipulation. The video illustrates the task of instruction following in the AlphaRed challenge. The arm is designed based on the Kinova Generation 3 modular robotic arm specification, bringing the simulation a step closer to the reality. The arm height is also adjustable. AI2SOAR provides egocentric RGBD images, as well as instance masks and 3D bounding boxes. The camera is mounted on the head. Its height and angle are adjustable. Other non-visual sensors include GPS and compass sensors to measure ego motion, and proprioceptive sensors to measure joint and end effector poses. Specially, AI2SOAR also provides a binary feedback signal to indicate whether a primitive action like opening, picking, or grasping is successful or not. The agent can take one of some predefined primitive actions for its base movement, like rotate left, rotate right, move forward, and others. The base movement is implemented by setting the pose of the virtual robot without physical simulation. The agent can also take one of some predefined primitive actions for its arm movement, like move arm X, move arm Y, move arm height, and others. The arm movement is implemented by solving the inverse kinematics. AI2SOAR also supports actions for the robot head to adjust the height and the pitch angle of the camera. For ISOR, the gripper actuator interacts with the object specified by the input mask with a predefined primitive action. For Manipulasaur, the gripper functions as a magnet, and an object can be snapped to the gripper. AI2Saur introduces 120 room scale scenes designed by artists, including different layouts like kitchen, living room, bedroom, and bathroom. It also provides over 100 object types, including rigid objects such as knife, and articulated objects such as fridge. Specially, objects are also associated with certain state changes. For instance, a vase can be broken, and the food can be cooked. Several challengers are based on ISOR. The Robosaur Challenger focuses on object goal navigation. The AlphaRed Challenger focuses on the grounding of language to actions. The goal is specified by a sentence. For example, rinse off a mug and place it in the coffee maker. The Rearrangement Challenger introduces a more challenging task, which requires the agent to rearrange the scene into the goal state. The agent can query visual observations relevant to the goal state and compare them with the current state. For tasks including object interaction, we can measure the success by checking the difference between current and target object poses, or checking the state of target objects. Manipulasaur currently supports a mobile manipulation task named PointNet. The goal is geometric, specified by a 3D position of the target object. Success rate without disturbance or collision is a newly introduced metric. It penalizes the agent which accomplished the task with unnecessary interaction. Last, we study ManyScale, which is proposed by SULab at UCSD. It features physical manipulation and object-level generalization. The video illustrates these two features. The robot consists of a mobile platform, a torso, and 1 or 2 arms. The mobile platform supports XY plane translation and Z-axis rotation. The torso has 1 degree of freedom to adjust the arm height. RGBD images and semantic masks are provided. Specially, ManyScale uses 3 cameras mounted on the top to provide a panoramic view. Other non-visual sensors include proprioceptive sensors for joint positions and velocities, as well as GPS and compass sensors for ego motion. Besides, it provides a point cloud fused from observations of all 3 cameras. ManyScale uses a continuous action space, which corresponds to the target velocities of controllable joints. The actuator output is torques applied on joints to achieve those target velocities. Such an actuator is equivalent to PD joint velocity controller in robotics. It relies on 4 physical simulation without abstraction. ManyScale introduces 4 challenging manipulation tasks. The first 2 tasks are open cabinet door and open cabinet drawer. The objective is to open the door or drawer. The target link is specified by the semantic mask. The other two tasks are push chair and move bucket. The objective is to move the target chair or bucket to the goal position. The goal position is specified by a visual indicator, either a red point or a white platform. The agent needs to infer it from observations. Many skill uses 162 objects over 4 categories from the PointNet mobility dataset. Large diversity of articulated objects is one of its features. Moreover, we would like to discuss some soft body tasks beyond the rigid body simulation. Many skill is going to introduce soft body oriented tasks. The embodiment is the same, except for specially designed end effectors. We will focus on goal specification in the following slides. The task writer is to write a target shape in a clay with the stick mounted on the robot hand. The goal is specified by a top view RGBD goal image to indicate the target shape to write. The task pouring is to pour a certain amount of water into the beaker. A red marker indicates the desired fill level. The task excavation is to excavate a certain amount of clay from the container with a mounted bucket. The target scooped mass is specified by a scalar. The task filling is to fill the beaker with some particles. The goal position to fill needs to be inferred from the placement of the beaker. The task rolling pin is to roll over dough to shape it into the target size. The goal is specified by a target bounding box of dough. To build a soft body-oriented environment in ManySkill, we gather different types of assets, including customized robot end effectors and rigid body containers. Soft body assets are represented by particles, and their physical properties have been tuned to meet our expectations. To summarize, different embodied AI environments have different levels of abstraction about the physical world, and are suitable for different tasks. Habitat 1 and eyesore are suitable for navigation, language grounding. Habitat 2 and manipulasaur are suitable for mobile manipulation. ManySkill focuses on physical manipulation and object-level generalization. We hope this tutorial will help you find a suitable environment to start your own journey with embodied AI, or have a better understanding about designing an embodied AI environment.
Hi everybody, welcome back to the part 4 of Building and Working Environments for Embodied AI tutorial. In this part, I'm going to introduce the experiences and practices to debug simulators. Simulations can produce many unexpected behavior. For example, the gripper may penetrate with the cube that it's trying to grasp. The robot may penetrate with the objects like the oven here. And for some complex mechanical structure, they may be simulated incorrectly, like shown in the third picture. And for some objects, the collision shape may look very different from their visual appearances. And in this section, I'm going to talk about how to debug and work with these kind of issues and how to improve the environments. In this section, first, I'm going to talk about how to identify potential problems when a simulation environment behaves unexpectedly. Next, I'm going to talk about how to debug and improve these environments. And this section is mainly for people with some experience in embodied AI. This section is divided into 6 topics: conventions in robotics, simulation assets, physical solver, renderer, controller, and some comments on environment speed. Let's get into the first cause of common bugs, the conventions in robotics. Here, I will talk about 4 topics: the quaternion representations, Euler angle representations, default quality frames, and joint order of different software and real robot. So, quaternion representations. As you may already know, quaternions are very commonly used to represent the rotation of rigid bodies in simulators. But there were 2 very common conventions in use in the popular software. The first is the XYZW convention, or vector Fritzler convention, where the XYZ component is placed before the scalar component of the quaternion. And this convention is used in ROS, PyBullet, PhysX, SciPy, and Unity. As you can see, they are all very popular software. And the second convention is the WXYZ convention, which is used in Sapien, Transform 3D, Eigen, Blender, Mujoko, VRAP, Pytorch 3D, and NumPy quaternion. And these are also some very popular packages. Since those 2 representations would represent different quaternions with the same 4 numbers, every time you use a quaternion, you should probably check the convention assumed in this library. If you think 2 conventions is not enough, here comes the Euler angles. We have 24 conventions, and those conventions are summarized in the Transform 3D library, as shown in the picture on the top right. And even for an XYZ convention for Euler angles, there are still 2 possibilities. One is the intrinsic rotations, or called the rotating frame. In this case, the coordinate axes of the Euler angles are assumed to be attached to a moving body. And there's also the extrinsic rotations, or the static frame, where the coordinate axes are attached to a static body. And sometimes in some libraries, they do not specify whether the static or the rotating frame is used. So you may want to test it before you use the Euler angles in those libraries. Next, default coordinate frames. Here is a concrete example where you will encounter while using Blender and Sapien. We model something in Blender, for example, this monkey in Blender. It looks upright. But then if you export this as an OBJ object and then import it into Sapien, this monkey would be facing up. So what's going on in the process? Well, it turns out different software and file formats would use different coordinate frame conventions. Here, Blender's OBJ exporter would change the frame by default. Since Sapien does not make frame assumptions based on file format, the orientation of this model will be changed after exporting from Blender and loading in Sapien. In fact, there are many different conventions to represent the orientation of objects and cameras. And here is a list of some of those conventions. And note, these are just some common choices, and they're not always true, and in many cases can be customized. And the general tip is that we should always visualize and inspect the loaded models when using assets from a new source, because we do not know about the default quantity frame convention for those models. Finally, the joint order of robots. So sometimes, even with the same URDF, different software can parse the joint orders in different ways. And here is a common scenario. First, you will train an RL algorithm to control a robot in a simulator. And the address space for this agent is defined as the joint velocity or position or joint force. Next, you will try to deploy this RL policy on a real robot. And here the issue is that the joint order on the real robot may be different from the joint order on the simulated robot. So in that case, if your algorithm does not work, maybe do not jump on to blame the sim-to-real domain gap. Maybe it's just a simple bug on the joint order. Okay, let's move on to the next topic, simulation assets. In this section, I'm going to talk about the following. The first is the gaps between collision and visual mesh. Next is that the collision of objects may be changed after loading them. Next, I will talk about issues arise when there are objects with very small mass or inertia. Then it's self-collision from bad modeling. And finally, issues with empty robot links. So first, gap between collision and a visual mesh. For robots, they often provide two types of meshes. One is the visual mesh, which are used for rendering only. And they're typically very fancy looking. And then there's also the collision shape, which is for simulation, especially for collision detection in the simulators. And these meshes are typically low poly and often convex. So what you see is often not used for collision checking. So sometimes when you see two objects are not visually touching, but they seem to be interacting, maybe you need to check their collision shapes. And down here is a snippet from the Franca Pandas URDF file. And we can see there are different visual and collision meshes loaded. And actually, let me run it in Sapien for a visual comparison. Here in the Sapien viewer, I can simply select this Franca Panda robot arm and then enable the collision shape. As we can see, the collision shape is quite different from the visual shape. So that's something important to keep in mind. Let's come back to the presentation. The next issue is connected with the previous one. That is, the collision shapes of objects may be changed after loading. And here is a real issue posted to Sapien GitHub. So a user loaded this oven into PyBullet and placed a cube into this oven. Here, the cube is shot out with seemingly no collision. As from the previous slide, you can probably guess that the visual shape and the collision shape are not matching. But in this case, they're actually the same shape. And I can even reproduce this exact issue in Sapien, which is a completely different framework compared to PyBullet. And let me show you the results. here I have the simulator paused. If I unpause the simulator, as you can see, this red cube will be shot out. So what's going on here? It turns out most simulators would require convex collision shapes to do the simulation. So they will take the convex hull of the provided collision shapes. So in this case, this oven is completely solid because it's taking the convex hull of the shape. And let's take a look again at this simulation. Here, let's enable the collision shape of this oven. As we can see, it's just a solid block. So this cube would easily shot out. And the solution to this case is to use an approximate convex decomposition algorithm to decompose this kind of visual shape into many convex parts so we can do the collision detection. And VHACD is the most common choice, and this algorithm is built into PyBullet. In our lab, we've also developed a collision-aware ACD algorithm that would preserve detail structures better. And for the links of these algorithms, I put them down here. Now, let me load the convex decomposed shapes and run the simulation again. Here, I'm just switching now to a decomposed URDF file. Now, when I run the script, you can see when I non-pause the simulator, this cube is not shot out. And this is from the collision shape. We'll see it's making much more sense compared to the previous case. Let's move on to the next issue that is caused by small mass or inertia. So sometimes a loaded object does not respond to any applied force or torque. And in this case, maybe it is because the mass or inertia of this object is just too small, and the simulator may choose not to simulate it, or maybe the floating point error is too large and the simulator cannot handle it. Here, I have a script for that. Here, I'm setting the density of this robot to be very low. So these two robot fingers would have an extremely small inertia. Let me try to drive these fingers. Here in Sapien, I can easily drive these fingers by sliding this slider here. And as we can see, I'm trying to drive this finger, but it's not moving. And that's not expected behavior. But here, I'm printing the inertia of those fingers. As we can see, they are very small. And to solve this issue, we can simply try to increase the mass and the inertia to see if the object starts to behave. And I would recommend trying to make the mass and inertia greater than 1e minus 7 scale. Here, let me open this file. Here, the density is set to 0.1, which is much lighter than air, and we do not want that. For example, if we change the density to 10, which is still very light, this robot can be simulated correctly. Let's see. Here, if I choose this finger, and then try to drive it, as we can see, from the values, this finger is indeed moving. Okay. The next issue is the self-collision from bad modeling. Here, you need to remember that the URDF files from GitHub may not be perfect. So sometimes if you just download some URDF file from the GitHub and load that as a robot into your simulation environment and then run some algorithms based on it, your algorithm may not work. And that is not because you are using a bad algorithm. Maybe this model itself is just not behaving well. For example, in here, we have downloaded a Allegro hand from GitHub somewhere. And this URDF file is having some self-collision that's not ignored. So we've provided a check URDF.py file that can detect such incorrect modeling. And by running this script, we will highlight the parts of the URDF model that is in collision at the initial state. So we can catch some intrinsically unstable behavior here. And this file will be provided in the same repo as the other scripts. So the takeaway here is that when using the URDFs provided by other people, maybe we should first check they are in a good shape and resolve any undesirable self-collisions. Okay, the final topic of this part is empty robot links. In many URDF files provided by the manufacturers of robots, there may be some empty or dummy links. For these links, there were no geometries attached to them. And they are often used as like connectors between non-empty links. Or sometimes they are even just used to indicate a frame in the space. But for this kind of empty links, they may cause problems in the simulators. For example, they may add additional method inertia onto the robot. Here, for an empty robot link in the URDF file loaded by PyBullet, it will actually give it a mass of 1 kilogram. And also, it will spit out a warning to your console. Well, for a typical robot finger, they are actually about 0.01 kilogram. So 1 kilogram would completely dominate the dynamic behavior of this robot finger. And that's definitely something we do not want in the robot modeling. And this kind of behavior is very common. For example, for the official Franka Panda link, there is a link 8 that does not have any geometry, and we need to look out for that. Okay, the next session is on physical simulators. I will talk about 4 common bugs. One is on simulation reset, and next is about undesired penetration. And then next is unstable grasping. And then I will summarize with some notes on contact properties. So simulation reset, I will first just run this reset script and see its behavior. So here I'm just throwing a white cube onto the stack of colorful cubes. Now, if I unpause the simulator, this thing is supposed to be reset. Let's see. However, it looks like every time we reset the simulation, it's a different one. But we should expect the behavior of the simulator to be exactly the same when we reset it. So what's the problem here? It turns out here we're only resetting the position, but not the velocity of the objects. And that is a very common bug in simulation reset. Now, let me also reset the velocities and let's observe the behavior. As we can see, every time we will repeat the same simulation process, they will look very, very similar. So in resetting simulation, we should always remember to reset everything, including positions, velocities, and constraints, such as controller parameters and controller targets. And the other thing to note is that the simulation is not always deterministic. Resetting and replaying may not result in the same outcome. And this behavior is caused by the iterative constraint solvers in simulators. So I mentioned this non-deterministic behavior here just to make sure that you do not chase after some bug that does not exist and that's caused intrinsically by the solvers of the simulators. The next topic is the undesired penetration. Here, I'll run the script that's stacking several cubes together. So here I have the simulation paused, so we can single step this thing to see their behavior. Let me make this cube transparent, and let's single step the simulation. As we can see, the cubes above would penetrate into this cube, causing some unstable behavior. If I just let the simulation run, the stack of objects would fall down. However, I initialized these objects in a perfectly straight line, and they should not fall down if the simulation is done correctly. So what can we do about it? It turns out we're using the time step 1/60. If we just decrease the time step to 1/120, the stacking process will be much stabler. Let's take a look. So here, as we can see, the penetration of these two cubes is already quite a bit smaller compared to the previous case. And if I just unpause the simulator, the stack is quite stable. So the most important parameter to make the simulation more stable is the time step. However, the smaller time steps would also mean a slower simulation, because to simulate the same amount of real time, you will need to step the simulation more times. And another important parameter is the solver iterations, as we have mentioned before in the constraint solver section. And here, for the gripper to grasp this red cube, if we set the max solver iterations to 2, it will very easily penetrate into the cube. But when we set it to 5, the gripper can actually grasp this red cube correctly. And the next thing is about grasping stability. Sometimes when you're trying to grasp something into the scene, like this cube here, you will see the gripper would slip off this object. And in this case, the most likely cause is actually that the friction or the normal force is just not enough to grasp this object. And to debug this kind of behavior, you can simply increase the friction to a very large number and see whether this grasping would be successful. And there are also other possible reasons. For example, we have too large of a time step, or the solver iterations are too small, as mentioned in the previous slide. Finally, I have some comments on the contact properties. So many people are not clear about the definition of a contact. In a lot of simulators, contacts would refer to objects with distance smaller than a threshold. So the objects may not be touching, they're just very close. And for those scenarios, the simulator would already call them a contact. But many people would like to only look at contacts where the objects are actually touching. So in that case, it would be better to check the contact forces, because like only touching contacts would have forces between the objects. So this image below shows a contact considered by the simulator, but the objects are not touching. And this is just something important to keep in mind. Okay, the next topic is the renderer. For the renderer section, I will describe 5 things. One is the definition of depth map. The next is the renderer for the depth buffer. And then depth of transparent objects, point cloud from depth, and matrices in vision and rendering. Let's get started from the depth map. In fact, there are many possible ways to provide the depth map. 2 common ways are the z-depths and the ray depths. Here, the z-depths means the distance along the camera axis. And this is actually the most common representation of the depth map. And the z-depths may be positive or negative. And the other representation is the distance or the ray depth, which is mostly used in ray tracers. And that is the distance along the camera ray. So in the image, the bottom right image, we can see the distance or ray depth is the segment connecting the camera center and the object, but the depth is that distance projected to the z-axis of the renderer. And in fact, for the z-depths, there are also different representations. For example, there's the z-linear depths and the z-buffer depths. For the z-linear depths, that refers to the distance along the camera axis, as we have talked about before. However, there's also the z-buffer depths, which is the raw depths from the renderer depth buffer. In most renderers, the depth buffer are not using a linear distance. Instead, the depth buffer or the z-buffer is often storing numbers in the range of 0 to 1, and they are not linear with the actual depths. And to convert from the z-buffer depth to a linear depth, one will use the formula I shown below. So essentially, it is a linear interpolation of the 1 over the near clip plane and 1 over the far clip plane, and then interpolate that with the buffer depth. By taking the reciprocal of that, we will get the linear depth. And note, this is only the most common choice, and there are other conventions used in renderers. So you should really just run a test when you are not sure whether this depth formula is used. And the next topic is the depth of a transparent object. There's often this question that whether we should include or ignore the transparent object in the scene. For example, for some barely transparent objects, maybe we want to include them. But for something like a transparent window, it's almost not there, and maybe we want to discard that object when we compute the depth. And most environments would include the transparent object, but in Xception, we recognize both use cases, so we will render both depth maps and let the user choose which one to apply in the applications. Next is on the point cloud from depth. So in many environments, we want to represent the observed images as point clouds. However, converting depth maps to point clouds is not always easy, and I will explain those in the next few slides when I talk about matrices. Here, my general tip is that first you should just look for a built-in API that would get you the point cloud directly. And most environments would actually provide that. And it's most safe to just use the provided API. But sometimes maybe you have to do it by yourself. In that case, always visualize and inspect the point clouds converted from the depth map. For example, with the TriMesh or Open3D libraries, they can draw some very nice point cloud visualizations that you can use to see whether you converted them correctly. So next, let's see why converting depth maps to point clouds are so hard. To talk about that, we need to understand the matrices in the vision and rendering conventions. The vision community and graphs community would use different matrices to represent the camera. For example, in graphics, we will use model matrix, view matrix, and projection matrix. While for vision, we will use the extrinsic matrix and intrinsic matrix. So next, let's see their connections and differences. First, the coordinate axis convention for the rendering and vision community are often different. For example, in OpenGL, people will typically assume that the forward of the camera is the negative z-axis, while the upward is positive y. But for like vision libraries, such as OpenCV, the forward would be positive z, and the upward direction would be negative y. Next, let's see the connections between the view matrix and the extrinsic matrix. First, I need to talk about the model matrix, which is in the rendering convention, and it will represent the camera pose in the world frame. The view matrix is just the inverse of the model matrix. We can use the view matrix to transform points in the world frame to points in the rendering camera frame. And this may be very familiar for vision people, as the extrinsic matrix would also transform points in the world frame into the camera frame. So the extrinsic frames is essentially the view matrix, but in the vision convention. But do note, the rendering camera and the vision camera would use two different frames. So this matrix would be kind of different in that sense. The next pair of matrices to compare are the projection matrix and the intrinsic matrix. For projection matrix, it would project points in the rendering camera frame into the normalized device coordinates, or the NDC frame. And for most rendering applications, such as OpenGL, the NDC would be a unit cube. But sometimes the depth dimension or the debuffer is the range of 0 to 1 instead of the range of -1 to 1. And for vision, we're more familiar with the intrinsic matrix, which will project the points to image coordinates with a linear depth. To connect the NDC frame and the image coordinates, we would first use a linear viewport transform to convert the XY dimensions, and then we would use a depth conversion as introduced in the previous slide. Here are the forms of the projection matrix and the intrinsic matrix. As you can see, they are quite closely related with some sign flips and some scaling. And note for the projection matrix, there is a near clipping plane and the far clipping plane. And those are unique to the rendering cameras where we have the frost assumption. Another thing that makes the conversion of depth maps to point clouds so hard is that different rendering software would not agree on which projection matrix to use. And here, I listed two different projection matrices used in different rendering software. For example, most OpenGL people would use the matrix on the upside, but for example, in Sapien, we would use a Vulkan renderer, and people typically prefer a different projection matrix in this case. So I would say we should avoid the projection matrices whenever possible. But if we want to convert a depth map to point clouds, we cannot avoid it. In that case, we should really perform extensive testing to make sure we get every matrix correctly. And in the slides above, I've introduced many transformations, like conic frame conventions and those transformations used in vision and rendering. And here I will have an image summarizing all the transformations, and you can refer to this slide after the tutorial to get a big picture. Okay, the next thing I'm going to talk about are the bugs in controllers. And here I will have 5 topics. One is on the special grippers with non-parallel motion, and then about position controllers. Next, it's balancing passive force. And the next topic is anti-factor controllers, some stable motions in anti-factor controllers. And finally, the joint limits in controller design. For some grippers, such as the robotic Q gripper, it will have some non-parallel motion generated from 6 interdependent joints. However, by loading some uractive files directly into simulators, we will typically get dependent joints as shown in the video down below. And the issue here is that the mechanical constraints is often not well modeled in URDFs, and different simulators would have different ways to simulate such loop constraints. So for these kind of grippers, we will want to manually add some constraints after loading these models. For example, here, for this robotic Q gripper loaded in Xception, we have manually added a position constraints to connect the inner part and the outer part of the fingers together. So we can model these kind of loop constraints correctly. However, do note that for these kind of loop constraints, they may bring a little bit of instability into simulators. So you should always be cautious about using such tricks. And the next topic is about balancing passive force. And we sometimes get the question that my robot never reaches target positions. Are my PD controllers bad? Well, in this case, I would say the most common issue is that the users are using the PD controllers instead of the augmented PD controllers as introduced in the section 2 of this tutorial. For PD controllers, the target is only reached when there are no other forces. For example, when there are no gravity, then there will not be any steady-state errors with PD controllers. But when there is gravity, we want to use the augmented PD control, where essentially we are applying additional joint force or torque to balance the passive forces along with the PD controllers. So in that cases, simulators would be able to achieve a zero error state with the PD controllers. The next topic is position controller and set position. Many people would confuse these two ideas. For a position controller, we are really saying that we are using some sort of controller, like a PD controller, that takes the position signal and then outputs the force and torques that are used to control the robot. This type of controller will respect physics. But when we are saying set position, we're really just teleporting the robot to whatever configuration we tell it to. In this case, this robot will reach the configuration no matter what, even if there is collision on the way. Here we illustrated these two types of position signal on the right. So for a position controller, the robot will collide with the environment normally. But when we are doing setting position, this robot will just be teleported into the door, which is not realistic. during dynamic simulation, we should in general never set the position or pose of the objects, unless we're just doing some sort of initialization. And next, when using the anti-factor control or EE control, sometimes we would observe some unstable motion of the robot arm. It would appear to be shaking at times. And this kind of effect is mostly due to the instability in IK solving. And possible solutions to this problem include increasing the control frequency or increasing the damping of the IK solver. We have provided a script showing the effect of the damping in the IK solver. And in the right videos, we can see increasing the dampings of the IK solver will help stabilize the arm motion. Next, the joint limits in controller design. Sometimes the robot anti-factor does not move as desired. Even if we tell it to move to a certain direction, it may not be able to do so. And this is often caused by the joint limits. Since most IK solver or EE controller does not consider a joint limit, when the robot reaches a certain joint limit, the anti-factor controller may not be able to move to certain directions. So in general, we should avoid reaching joint limits in the algorithm design. And here, as we can see, we can use the CVPR viewer to see the joint angles of the robot and figure out which joints are at its limit. Okay, so finally, I'm going to give some suggestions on debugging or improving the environment speed. Environment speed is a very common issue that comes up a lot. I would say in general, optimizing the environment speed is quite hard. So I will only give some general guidelines. First, we should debug the environment speed in a single process or single thread to avoid unnecessary complications. And second, I would suggest using a profiler. And we need to profile the following things. The first is the total time for stepping the simulation. And the next is the total time for doing the rendering. And we should also keep track of the time for expensive planning or narrative evaluation. And of course, we will also record the time for the other things in the code. So for this tutorial, I'm not going to show a detailed walkthrough of some profiler, but here I've provided a link to a very good tutorial on the visual profiler provided by the Habitat environment. And they use the PySpy for the Python code profiling and NVIDIA's nSight for CUDA profiling. And the great thing about this tutorial is that their approaches can be applied to any other Python-based environments. As for Sapien, we would provide the option to compile Sapien with Easy Profiler, which would provide some profiling results for C++ functions that are normally hidden from the Python side of Sapien. After we do the profiling, maybe we'll figure out that rendering is the bottleneck of the environment. In that case, I would suggest first checking the loaded meshes. If there were meshes with like millions of triangles, those kind of meshes will make the rendering a lot slower. And also, you need to check for the number of rendered objects. If you want to improve the rendering speed, my suggestion is to switch to a lighter renderer. For example, if you do not need the RGB images and you only need depth of objects, maybe you can switch to a depth-only renderer that can often save a lot of time and memory. Next, if you find out that the physical simulation is actually the bottleneck, I would suggest following these checks. The first is that if you find that a single step is consistently slow, in that case, it could be caused by undesired collision. For example, we've mentioned in the previous case where the robot has some self-collision that's in its initial state that we do not want. And those kind of self-collision will make the simulation a lot slower. And next, though, we should also inspect the number of objects in the scene. If there are many objects, the simulation will also be naturally slower. Next, if the physical simulation speed varies across multiple steps, what you may need to watch out for is that certain steps may have a lot of collisions and certain steps may not have a lot of collisions. And to speed up the slow steps, like before, disabling unnecessary collision checking may help the speed here. Okay, to summarize, in this section, we've seen some tips to debug problems in conventions in robotics, simulation assets, physical simulator, renderer, controller, and I've given some tips on the environment speed. Here, if you have any questions regarding this tutorial, you can contact me with my email. And I would also like to hear about your story on debugging environments. And if you think there's something I'm missing here, you can also let me know and to help me improve this tutorial in the future to include more tips and ways to debug simulators in embodied AI environments. Okay, thank you.
Hello everyone, welcome to the fifth part of the Building and Working Environments for Embodied AI tutorial. The topic of this section is Real Robot and Sim-to-Real. I'm Richard from Tsinghua University. My research interests include 3D sensing, computer vision, and robot learning. Currently, I'm working closely with House Group on Maniscale 2022 and its Sim-to-Real problem. In this section, we are going to talk about sim-to-real gaps for robots and how to mitigate these gaps. This section is mainly for people who would like to deploy embodied AI in the real world. This is the outline of this tutorial. Firstly, we will introduce the challenges of deploying policy in the real world and the suggested pipeline. So let's get started. Assume that we already have a policy pipe trained in the simulation environment, which takes visual signals as input. The goal of Sim-to-Real is to deploy this policy to the real robot. But it's not an easy thing to do. There are many factors you have to take into consideration that may cause the Sim-to-Real gap and limit the policy's transferability. To name a few, the robot communication, robot actuator accuracy, sensor noise, mismatch of the world model, the software and hardware implementation of the robot controller. In order to give you a concrete sense of these challenges, we will show some examples for each kind in the following slides. First is the robot communication latency. In simulation, the action or command we give will take effect instantly, but for real robot, there will be a control latency. It could be 0.1 second for some robots. In most cases, it doesn't matter, but you should take it seriously if you aim at high precision control or high dynamic control. What's more, in simulation, we can suspend the simulator when we generate the sensing signals, feed them into the policy network, and get the next action. But the real world never stops. It will continue running when you do all the things above. You should keep this in mind, especially when you are using velocity control or torque control. Another factor that is usually not modeled in the simulation is the deformation of robot components. For example, the robot fingers may deform during grasping, which will influence the grasp stability. Another important factor is the sensor noise. For proprioception, the joint positions of real robots are acquired from encoders and are usually accurate, but the joint velocities are computed from differentiation and are usually noisy. For some real robots, we can get the joint torque signals, but there could be a large symmetrical gap due to the sensing technique in real. For the environmental sensor noise, the difference of visual signals between simulation and the real will significantly influence the transferability of visual policies. I'll introduce it in detail in the second part. When we build a simulation environment, we always introduce some kind of model simplification for computation efficiency. So, there are some phenomena that are not modeled in the simulator and will cause the world model mismatch. For example, jerk is the rate of the acceleration changes. Due to the power limit of real robot actuators, the maximum value of jerk is limited. But most robot simulation environments do not consider this limitation. However, it can be an important factor for high dynamic scenes. Besides the physics model, the geometry and dynamic parameters can also be different between sim and real. Some of these errors can be eliminated through system identification. Besides these sensing and model gaps, there are also some symmetrical gaps in controller implementations. In simulations, we can use all kinds of controllers like position control, velocity control, and torque control, and change the controller parameters freely. But in the real world, the provided API are different for different robots. For example, for some robots, we can set the PD parameter of controller, but for some robots, it is restricted. Also, some robots like Franca provide the torque control API, but it needs to run at high frequency with low latency for stability. Given all these symmetrical challenges, we suggest that you take a three-step approach to address challenges progressively. First is to deploy joint trajectory following. Second is open-loop policy replay. And the final is closed-loop execution. The goal of joint trajectory following is to check the communication and accuracy of the real robot. Assume that we have a policy pi, which is trained in the simulator. We first roll out the policy in the simulator to get the trajectory. Then we extract the joint positions from the trajectory and conduct trajectory following on the real robot. If everything is okay, the motion of the real robot should be the same as the one in the simulator. The reason we conduct joint trajectory following first is that basically all real robots support joint trajectory following, and the joint position controllers can avoid accumulation of execution errors. Moreover, while the joint position control is simple, it is sufficient for tasks in static scenes, such as simple grasping. For this step, if there is a big difference between sim and real, the most likely cause is there are some implementation bugs. You need to debug the communication and the controller before go to the next step. The second step is open-loop policy replay. The goal of this step is to check the controller of the policy action space on the real robot. While the joint position controller is sufficient for tasks in static scenes, using other action space and corresponding controllers, such as Cartesian position control, velocity control, and variable impedance control, may lead to faster or more stable policy learning and better performance. Assume we have a policy pi obtained from the simulator. We still first roll out the policy in the simulator to get the trajectory. But different from the first step, we use the robot action rather than the joint position from the trajectory and execute the action sequence on the real robot. The reason why we conduct open-loop policy replay as the second step is that the policy action space may involve some modules whose performance are sensitive to implementation details, which may be different for sim and real. For example, the output of the IK solver can be sensitive to the hyperparameters for kinematical redundant robots. So, in this step, the robot may fail due to issues in controller implementations, like model mismatch or wrong parameters. And since the policy is rolled open loop, there will be error accumulation along the task horizon. If you finish the first step successfully, the last step is closed-loop policy execution. The goal of this step is to check the influence of the visual gap. Still, assume we have a policy pi obtained from the simulator. This time, we do not roll it in the simulator. Instead, we roll it online on the real robot. First, we get the observation from real world, like RGB images from camera, depth map from 3D sensors, and robot pre-perception. Second, we feed them in the policy network and get the action. Second, we execute the action on the real robot. Repeat these 3 steps until the task is finished or we reach the max step number. The difference between this step and step 2 is that we use feedback from the real world to correct errors in policy execution, so we call it closed loop. However, since the input of the policy is the real signals, we will be badly affected by the domain gap, which will be addressed in the second part of this tutorial. Also, because we need to get the visual signals and run the policy online, the latency gap may be a big issue for non-static scenes. If everything is done correctly, now your real robot will be able to deal with dynamic scenes and be more robust than open-loop systems. Lastly, there is a small tip. According to our own experiences, most of the taps, the problem is not a symmetrical gap, but only a simple bug. So we suggest you follow the pipeline step by step and check the rules carefully before moving forward. Last but not least, carrying on experiments on real robots is much more dangerous than simulation. It may cause real damages to robots and humans. So, please always keep safety in mind and hold the emergency stop button when the robot is on. Here we show our experiment result on symmetrical object grasping. The trajectory can be accurately aligned between sim and real by following the pipeline above. Today, for the audiences in CVPR, I guess most of you are interested in using visual signals as input. Compared with RGB images that are widely used in different CV tasks, depth maps from 3D sensors contain geometry information of the scene, which are important for embodied AI's interaction with the world. So, for the second part, we will focus on real and simulated 3D sensors. In order to understand the source of domain gap of depth signals, we need to first understand the mechanism of real 3D sensors. According to working principles, commercial 3D optical sensors can be divided into depth by triangulation and depth by time of flight. The triangulation method includes passive stereo vision, active stereo vision, and structured light. Triangulation methods derive the depth of target by finding correspondences in observations from different perspectives. The correspondences can be derived in various manners. For passive stereo vision, the correspondences is derived by using photo consistency. Therefore, it requires textured surfaces and cannot mirror textureless objects. Active stereo vision sensors overcome this weakness by actively projecting a particular pattern onto the object surface. For structureless sensors, the correspondence between the camera and the projector is established by decoding the captured patterns. Time of flight method or TOF method estimates the target device distance by measuring the flight time of optical signals. The sensor consists of a light transmitter and a light receiver. The light transmitter emits modulated light onto the target surface, and the receiver senses the reflected light. The round-trip time can be measured directly or computed by signal processing. Today, we will focus on active stereo vision depth sensors. Compared with other kinds of sensors, it has following advantages. It is able to measure dynamic scenes and textureless areas. Also, because it usually works at certain spectral range, it is robust to environmental illumination. The sensor is also lightweight, which makes it suitable to be mounted as a robot end effector. However, it still has some limitations. This figure shows the depth map of 3 different objects. The measurement of specular and transparent objects are noisy and incomplete, which limits its application in certain scenarios, such as bin picking and object manipulation. Also, it leads to a large gap between simulation and real data. Currently, most existing embodied AI environments directly use the ground truth depth from the depth buffer. The advantages of this method is it is quite simple to implement and brings small overhead. But it doesn't model the occlusion or artifacts from specular and transparent objects, which makes it very difficult for policy trained in the simulation to transfer to the real world. The most straightforward way to narrow the sim-to-real gap is noise-based depth map augmentation. In the real work of learning to augment, it designed an efficient search for depth image augmentation strategy using object localization as a proxy task, and found the optimized combination of augmentation. However, the real depth sensor error pattern is usually complex and cannot be simulated by combining simple augmentations. Another way to narrow the domain gap is domain adaptation. In the PixelDA work, they generate the simulated depth images based on GAN. In theory, the GAN-based method can model the real error distribution, but in practice, the generated depths may not be physically plausible. In order to make the depth simulation physically plausible, it would be better to build a physics-grounded depth sensor simulation pipeline. Firstly, let's recap the mechanism of active stereo vision sensor in more detail. An active stereo vision sensor usually consists of an IR projector and 2 IR sensors. The IR projector shows IR pattern to the scene, and the 2 IR sensors capture the reflected pattern and compute the depth by stereo matching. There is also a RGB sensor to capture the texture information of the scene. In depth scenes in 2017, they first rendered the stereo IR images by rasterization and perform stereo matching on the rendered images. It can simulate the error caused by stereo matching, which narrows the sim-to-real gap for normal objects. But since it uses rasterization for rendering, it cannot simulate the complex length transport phenomenon of real transparent and translucent objects. In order to simulate the depth sensing result of transparent and translucent objects, we propose to render the stereo images by ray tracing, which allow us to simulate the transport of air light with high fidelity. We further model the sensor noise for real air sensors. Finally, we perform stereo matching on the images with noise to generate the simulated depths. As shown in these figures, by using ray tracing for rendering, we can simulate the light transport on transparent objects more accurately and generate the invalid holes very similar to the depth maps acquired by real sensors. But a physically accurate ray tracer and a realistic noise model enough to close the sim-to-real gap of depth maps? The answer is no. According to the rendering mechanism, the lighting and the object material have significant influence on the rendering results. So we need to acquire the lighting and project material of the real world to further close the sim-to-real gap. After all this works, we could generate simulated depth map with very small domain gap. Such depth sensor simulator can be helpful for many tasks. For example, 60 pose estimation. It is very difficult to get the precise 60 pose of objects in the real world. However, we can access it in simulation at no cost. In this experiment, we generate a large-scale 60 pose synthetic dataset using the proposed depth sensor simulator, trained state-of-the-art pose estimation network on the synthetic data, and directly tested on the real data. As shown in this figure, the network can estimate the 60 pose accurately, even for transparent and specular objects. But for a network trained on the rasterization images, it failed to detect the object in the real depth maps. If you are interested in our work, you could refer to the paper link and the documentation for more detail. That's all for this section. Thank you for your time.
Okay, let's get started in the last part of this tutorial. Embody AI tasks in many-skill and visual learning challenges. The many-skill benchmark is a generalizable manipulation skill benchmark with large-scale demonstrations created by our lab. We've gained many insights into embodied AI tasks and methods through hosting the many-skill challenge. And here, I would like to share these with you. In this section, we're going to talk about what kind of manipulation tasks are difficult. Imitation learning, RL, and classical robotics, which one can solve embodied AI tasks better for now? And I'll also give a preview of the many-skill challenge this year in 2022. First, let me give an outline. In this section, I'll talk about the many-skill benchmark and then summarize the many-skill challenge in 2021 and then provide the overview for this year. Let's get started into the many-skill benchmark. If we think about how humans learn to manipulate, we find that a remarkable feature of human manipulation is generalization. Once we have learned to manipulate a category of objects, we will be able to manipulate even unseen objects of the same category, despite the topological and geometric variations. Let's take the swivel chairs as an example. No matter how many wheels the chair has, or whether there were armrests or a headrest, what the shape of the backrest look like, we humans can use them immediately, right? We refer to such ability to interact with unseen objects within a certain category as generalizable manipulation skills. Generalizable manipulation skills are quite hard to obtain because we need to generalize over object geometry, topology, and appearances. For example, to manipulate swivel chairs, we must handle test chairs differently from training chairs. This probably requires to discover some sort of knowledge about object structure, like part, key point, or skeleton. Having explained the generalizable manipulation skills, now we can finally answer the question, what is many-skill? To summarize, many-skill is a benchmark for learning generalizable manipulation skills. It features 4 challenging manipulation tasks: diverse articulated objects, egocentric 3D visual inputs, and large-scale demonstrations. Let's dive into the details about each feature one by one. First, many-skill currently includes 4 different physical manipulation tasks, each targeting a distinct challenge. In the open cabinet door task, we have a robot arm installed on a movable platform, and it needs to open the door of a cabinet. This task exemplifies motions constrained by a revolute joint. In the open cabinet drawer task, a robot arm is required to pull out the drawer of a cabinet. This task exemplifies motions constrained by a prismatic joint. Note here, we do not restrict the ways to open the drawers. You can either open it by grasping the handle or by dragging the side of the drawer, as long as the policy can reach the desired goal state. In the push chair task, two robot arms need to collaborate and push the chair to a target position indicated by a red ball. This task exemplifies motions constrained on the plane through wheel-ground contact. This chair is a swivel chair, and it generally has many joints, resulting in complex dynamics. Therefore, it is a little difficult to solve push chair by motion planning and favors learning-based methods. In the move bucket task, two robot arms collaborate to lift a bucket and move it to a platform. Note that there is a moving ball in the bucket. This task exemplifies motions without constraints. However, this task is still very challenging because it heavily relies on two-arm coordination, and balancing the bucket ball system is also difficult. Then, let's go to the second important feature of many-skill, diverse objects, which are necessary for learning generalizable manipulation skills. Most existing robot learning environments usually lack the diversity of 3D assets. So we have included a large variety of 3D articulated objects in our benchmark, with 162 objects over the 4 tasks in total. Each object is processed and verified to support manipulation. The third feature of many-skill is egocentric 3D visual input. Many-skill supports 3D visual inputs via point cloud or RGBD, which are captured from a simulated panoramic camera mounted on the robot. The 3D visual inputs allow various computer vision models to be applied. Lastly, we have also provided a large number of high-quality demonstration trajectories. For each training object of each task, in total, there are around 36,000 demonstration trajectories and over 1.5 million 3D video frames. With these demonstrations, researchers can then spend less time on collecting good trajectories and instead focus more on other interesting aspects of the problem, such as network designs and learning algorithms. Now we have introduced all the significant features of many-skill benchmark. The next question is how to use this benchmark. Basically, our training evaluation protocol is quite similar to that of supervised learning. We split the objects from a single category into non-overlapped training sets and test sets, then build the training and testing environments respectively. For each task, the agents should be trained based on the training environments and the provided demonstrations, and then they are evaluated on test environments. The performance metric of an agent is the mean success rate over all tasks. During the development of many-skill, we found that some interesting research problems have emerged. For example, how to design better networks for physical manipulation. Our recent experiments show that sparse ConvNet actually achieves better training and test performance than the baselines, which means better network architecture can indeed help manipulation. In addition, many 3D shape analysis techniques can also be utilized, such as key point extraction, part discovery, and others. There are so many possibilities to explore. On the learning algorithm side, it's also interesting to study how to combine offline demonstrations with online learning. When learning from demonstrations, how to solve the multi-modality problem. And also, during manipulation, we found that the object can be partially occluded, so the manipulation cannot proceed. In this case, maybe we need to actively control the perception module. In a word, we believe there are so many interesting research problems in the many-scale benchmark. Next, let me give a summary of the Many-Scale Challenge 2021. In Many-Scale Challenge 2021, we have given out a total of $20,000 of awards, and we prepared 3 challenge tracks to accommodate for participants with different backgrounds, such as computer vision, reinforcement learning, and robotics. The challenge award ceremony was held on the ICLR 2022 workshop, Generalizable Policy Learning in the Physical World. This workshop has also received many works on generalizable policy learning, which can be accessed through the link here. To accommodate for participants with different backgrounds, our challenge is arranged into 3 tracks. In the no interaction track, participants are provided with demonstrations to build agents. No interaction with the environment is allowed. In the no external annotation track, both demonstrations and interactions are allowed, but no external annotation is allowed. And this is a track like a common setup for reinforcement learning. In the no restriction track, participants are encouraged to solve the problems using any methods. Note that these methods must work with objects which are not seen before, which is also difficult. After the intense preparation of the challenge by the organizing team, we launched the challenge on July 29, 2021, and over 40 teams registered, and after over 5 months of competition, 7 teams have received final awards. The winning teams have been announced on the workshop. Next, let me summarize the major results from the Many-Scale Challenge 2021. Let's first check which track is the most difficult. Consider that even learning policies on the training set is challenging. We use a metric as averaging the training set performance and test set performance, gives them 50% weight for each. So under this metric, for each track, we can compute the average score across all tasks. See the results in the box plots, and here are what we can read from the plots. First, the no interaction track only allows learning from demonstrations. The methods under this track perform the worst, which consolidates the importance of the interaction for the policy learning. Second, where all kinds of techniques are allowed, the no restriction track has most of the tasks solved at a good performance. It also shows that the end-to-end policy learning methods such as RL cannot outperform carefully engineered systems using the classical task and motion planning pipeline, but the gap is not very big. Since the Many-Scale Challenge imposes the open source policy, we encourage everyone who is interested in the results to check the source code of the winning methods and learn more about the details. And next, let's check which task is the most difficult. We still use the metric that averages the training set performance and the test set performance. Under this metric, for each task, we can compute the average scores across tasks. See the results on the bar plots. And here are what we can read. First, the task Open Cabinet Drawer seems simplest. The major challenge is basic navigation and grasping skills, and both seem to be easy. Second, the task Push Chair seems to be the most difficult. Recall that the chairs are swivel chairs. Their dynamics model is very complex. Also, the agent needs to push them by the collaboration of 2 arms. For this undirectionated system to be manipulated by the 2-arm collaboration, the existing methods still cannot solve the problem very well. Then, let's analyze the generalization performance, which is the gap between the training and test performance for different tasks. This is very clear that the train test performance gap is quite big when interaction is not allowed. Therefore, we can see interaction can effectively improve the generalization when the shape difference exists across training and test data. Finally, let's analyze the generalization performance for different tasks. It's a little surprising that the open cabinet door task has the biggest train test gap. After checking the data, we guess it is mainly because many doors have small handles, and detecting these small handles from point clouds reliably is hard. And therefore, the visual perception generalization gap may have caused the policy learning gap. We will release a paper summarizing all the results from the Many-Skill 2021 challenge soon. Finally, let me give a preview of the Many-Skill challenge this year in 2022. Many-Skill 2022 will follow a similar format to Many-Skill 2021. The focus will be on object-level generalizability, and there will still be 3 tracks. In addition, we will add new tasks and provide a much faster system implemented with an optimized version of CVPR. In Many-Skill 2021, there were 4 tasks in articulate object manipulation. This year, we will have about 10 rigid body tasks, 5 articulated body tasks, and 5 deformable body tasks. And here are some GIFs showing the demonstrations collected on the 5 deformable body tasks: pouring, the breaker, filling, excavation, and rolling pin. We expect to launch Many-Skill 2022 in July this year. And please follow our group Twitter for updates. Okay, thank you all for listening to the CVPR tutorial. And here are the content information and some useful links.